Hi, Assalamualaikum and a very good morning. So now we are in chapter 10, which is carboxylic acid, and we're going to focus on the subtopic of 10.3, which is physical properties. So in this video, we're going to look and explain into the physical properties of the carboxylic acid, where we can explain them in terms of the boiling point, as well as by doing the solubility in water and in organic solvent. Also, we're going to explain the acidity of the carboxylic acid in comparison with alcohol and phenol. Last but not least, we're going to look into the halogenated carboxylic acid, and we're going to compare them based on the number of the halogen group as well as the position of the halogens. So without any further ado, let us start. So for the boiling point, the carboxylic acid will have the higher boiling point than alkenes of a similar molecular mass. So this is because of the ability of the carboxylic acid to form the intermolecular hydrogen bond and the ability of the carboxylic acid in order to form the hydrogen bonded dimers. So carboxylic acid will have the ability to form dimers where they are arranged closely together. So the structure of dimer is as shown here, where there are two carboxylic acid that arrange closely enough together, and they're gonna make a hydrogen bonded dimer. So it almost look like a cyclic structure when the carboxylic acid molecules are close enough together. And then they're gonna have their intermolecular hydrogen bond at above and below in order to connect the two structure together. Okay, and this causes the hydrogen bond in the carboxylic acid dimer to be relatively stronger. Hence, more energy is needed to overcome the intermolecular forces, hence causes the carboxylic acid to have higher boiling point. Alright, now we're going to talk about the solubility in water. So the carboxylic acid, which is represented by RCOOH here, with carbon number 1 until the longest carbon chain is 5, is completely soluble in water due to the ability of the carboxylic acid to form hydrogen bond with water molecule. So in the presence of water, the carboxylic acid do not dimerize. Instead, they form hydrogen bond with the water molecule. So let's say if you have a carboxylic acid here and here, so inside there, a beaker for example, but then you add a water, so the water gonna be in between the carboxylic acid molecule. So they're not gonna forming a dimer between them. Instead, they're gonna form a hydrogen bond in between the the water molecule here. Okay, so this is gonna form a hydrogen bond here, 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 and here as well. Okay, so now the solubility of carboxylic acid in water is almost similar to that of alcohol. So as the number of carbon atom increases, the hydrophobic area becomes larger and the solubility gonna decrease. So when carbon atom increases, solubility will be reduced. So this can be represented as here because this one is the hydrophilic area, which is loves water, but other group here, which is the alkyl group, is the hydrophobic area, hates water. So it makes it insoluble. Okay, so generally you can say that when the carbon chain less than 5, it is soluble in water. However, when the aliphatic carboxylic acid has more than 5 carbon, 1, 2, 3, 4, 5, then they are insoluble in water. Okay, but 5 here is still soluble, but if it is more than 5, for example, an extra one here, then it is insoluble. Okay, because of the hydrophobic area. And now for the aromatic carboxylic acid, they are slightly soluble in water at room temperature, and this insolubility, this slightly solubility here is due to the huge aromatic ring, which cause the hydrophobic area to be large. Okay, and for the dicarboxylic acid, they are relatively more soluble in water because they have two carboxyl group here, so they can form more hydrogen bonding with the water molecules. Okay, now we're going to look into the solubility in non-polar solvent. Okay, So the example of non-polar solvent is benzene. Just now we looked the solubility in water, okay? But now non-polar solvent, for example, benzene, okay? So carboxylic acid are basically soluble in non-polar solvents such as benzene. Okay, so this is due to the presence of the van der Waals forces between benzene and the alkyl group of the carboxylic acid. So let's say if we have a carboxylic acid here, and then we have a benzene ring, a benzene solvent in the beaker. So they're going to be forming a van der Waals forces in between the alkyl group of the carboxylic acid as well as the carbon of the benzene ring. Okay, and the van der Waals forces here causes the carboxylic acid to be soluble. And here are the bigger interpretation of the carboxylic acid with the benzene ring. So essentially, the carboxylic acid, when it is in the beaker, so the carboxylic acid can form hydrogen bonded dimer. Okay, so we need to use the term hydrogen bonded dimer, okay, not hydrogen bonded dimer. And then they have the hydrogen bonded dimer. At the same time, they will have the van der Waals forces. Okay, so they have these both together, hydrogen bonded dimer and van der Waals forces. This make it very soluble in the non-polar solvent. Okay. Now we're going to look into the solubility in polar solvent. So example of polar solvent here is the alcohol as well as ether. Okay, so the carboxylic acids are soluble in polar solvents such as the alcohol, and this is due to the formation of the hydrogen bond and the van der Waals forces between the alcohol and the carboxylic acid. So here is the carboxylic acid and here is the alcohol. Okay, and here is the carboxylic acid again. Okay, so what's going to happen here is that they're going to be forming a van der Waals forces in between alcohol and carboxylic acid group, and at the same time they'll also be forming the hydrogen bond. So there are two types of bond, thus also making it very soluble in polar solvent. Now we're going to look into the acidity of the carboxylic acid. So for the carboxylic acid, the carboxylic acid is going to be the most acidic class of compound that contain the carbon, hydrogen, and oxygen. And in this case, the carboxylic acid going to be more acidic than phenol, more acidic than water, and more acidic than alcohol. So, however, the carboxylic acid is still considered a weaker acid compared to the mineral acid that you know. For example, the sulfuric acid than NaHCl here, which is hydrochloric acid. So, basically the acidity of the carboxylic acid is influenced by two things. First is the resonance effect, and second is the inductive effect. So now let us look into the resonance effect first. So the resonance effects is basically when the carboxylic acid dissociate to form the carboxylic ion and the hydronium ion. Let's say if you have a carboxylic acid here, when it dissolves in water, what they're going to produce is the carboxylic ion as well as the hydronium ion. So the OH bond here going to be broken, and the hydrogen going to be transferred into the water molecule here in order to form hydronium ion. And this formation of the carboxylic ion here will form the delocalization between the two oxygen atom. So the negative charge here is movable in between the oxygen atom. And this causes the carboxylic ion to be more stable. So let's say if we have a carboxylic ion here, so the negative charge going to be transferred into this single bond here in order to form double bond. And the double bond here going to break apart in order to give negative charge on the blue oxygen atom here. Okay, and this is going to form resonance structure in between them because it is continuously happening in over a period of time. Okay, so the resonance structure going to be forming in between these two structures here, and we usually enclose it with a bracket to show that it is a resonance structure, and this shows the stability of the carboxylic ion. Okay, and now we're going to look into the inductive effect. Just now is the resonance effect. Okay, but here is the inductive. So inductive effect basically means that the substituent group attached to the carboxyl carbon. Okay, so it refers to the substituents that attach with the carboxyl carbon here, which is refers to this carbon. And it can be an electron withdrawing group, or it can be electron donating group. So the electron withdrawing group will basically increase the acidity. The electron donating group will reduce the acidity. Okay, so donating reduce the acidity, D and D. Okay, so basically the carboxylate ion, when it is attached with an electron withdrawing group, for example halogen group, chlorine, bromine, or fluorine, so the negative charge here gonna be pulled down will be pulled by the electron withdrawing atom, hence making it more stable, hence it is more acidic. So that's the general idea. And meanwhile, for the electron donating group, for example an alkyl group, for example CH2, CH3, CH2. So what the alkyl group gonna do? It gonna donate electron density towards the carboxylate ion here, and thus make it less stable because they have too much electron, hence less acidic. Okay. Okay, so that is why electron donating group reduce the acidity. Okay, nice one. Now we're going to look into the effect of the electron withdrawing group first. So the electron withdrawing group attached to the carboxylate ion will delocalize the negative charge on the oxygen atom. So it's gonna pulling the electron density towards electron withdrawing group, and this causes the strength of the OH bond decreases, making the OH bond weaker and easier to break. Because you know that initially the carboxylate ion, the carboxylic group, for example, here is the electron donating group, withdrawing group. For example, we have the Cl here. Okay, so initially the electron density gonna be pulled towards the chlorine through this bond here. Okay, and this causes the OH bond to be weaker because electron are keep pulling towards the electron withdrawing group. So the strength of the bond gonna be weaker, and hence the hydrogen will be easier to be released. Okay, so when it is easier to be released, the carboxylate ion will become more stable, and hence we can say that the acidity increases. Okay, and we can also say that when the number of the electron withdrawing group, so when we have a lot of chlorine atom, the acidity will increase even more. All right, so now let us look into the example here. So let's say if we have the 2-chloroethanoic acid, and here we have the ethanoic acid. Okay, so the presence of the chlorine atom, which is an electron withdrawing group, reduces the electron density of the OH bond. Okay, so the OH bond becomes weaker and easily broken, and H plus gonna be released much more easily. So we can say that the 2-chloroethanoic acid will be much more acidic in comparison to ethanoic acid. Now we're going to look into the number of the electron withdrawing group. So here we have a 2,2-dichloropropanoic acid, and here we have the 2-chloropropanoic acid. So as you will expect, the 2,2-dichloropropanoic acid has 2 chlorine atoms. Meanwhile, for the 2-chloropropanoic acid will only have 1 chlorine atom. So with more electron withdrawing group, the electron density of the OH bond is reduced much more greatly. Hence, the OH bond here will become weaker. So when it is become weaker, the hydrogen will be easily released. So we can say that the 2,2-dichloropropanoic acid is much more acidic comparison to the 2-chloropropanoic acid. Okay, now we're going to look into the effect of the position. Okay, kedudukannya. So the inductive effects are basically dependent on the distance. So the effect of the electron withdrawing group decreases as the substituent move further away from the carboxyl group. Okay, so chlorine here is much more closer to the carboxyl group. This chlorine here is further. Okay, so here we have a 2-chlorobutanoic acid. Here we have 4-chlorobutanoic acid. So the chlorine atom is nearer to the carboxyl group in the 2-chlorobutanoic acid, than in 4-chlorobutanoic acid. So we can say that the OH bond is weaker in this side, okay, because OH, so the electron are being pulled towards the electron withdrawing group, and hence the hydrogen gonna be easily released. So we can say that the 2-chlorobutanoic acid is much more acidic. Okay, now we're gonna change the substituent. Now we're gonna focus on the electron donating group. Okay, so here we have a methanoic acid. Here we have the ethanoic acid because of 2 carbon, and here we have propanoic acid. Okay, so the presence of the electron donating group, for example, alkyl group, will increase the density of the negative charge on the oxygen atom. Okay, so here is one. This one is the alkyl group substituent, and here is the alkyl group substituent. So here gonna donate electron density, here gonna donate electron density, and here gonna donate electron density. So this one is larger, so they wanna give more. This one 2, and maybe this one 1. Okay, so the larger the size of the electron donating group, the higher the electron density of the OH, because the alkyl group keeps donating the electron density towards OH side. So making the OH bond here become very strong. Okay, stronger the bond. So when it is strong, the hydrogen is very difficult to be released. Okay, very difficult. So we can say that the propanoic acid gonna be the least acidic. So the methanoic acid gonna be the most, followed by ethanoic acid and the propanoic acid. So here is the least acidic propanoic. Okay. And here are the summary of the inductive effects that I've taught just now. So you can read this letter by your own. Okay, so the example of the electron withdrawing group, halogens, for example, chlorine, bromine, or fluorine. Meanwhile, for the electron donating group can be alkyl or aryl. Okay, so now we're going to look into the acidity of the carboxylic acid, phenol, and alcohol. So as mentioned, the carboxylic acid are stronger acid compared to phenol and alcohol. Okay, so here gonna be carboxylic acid gonna be more acidic than phenol and more acidic than alcohol. Okay, this is because the carboxylic acid, when dissociated in water, they're going to form a carboxylic ion. So this negative charge can be transferred here, and this can be transferred here. Okay, and it can form resonance structure. Meanwhile, for phenol, it can form phenoxide ion, and alcohol can form an alkoxide ion. So you have looked about this one in the subtopic of 8.5 in the chapter of hydroxy compound, in the subtopic of phenol. Okay, so for the phenoxide, it can delocalize the negative charge inside the benzene ring. Okay, so here will enter here, here will enter here, and so on. So you can make a lot of resonance structure. Okay, and for the alkoxide ion, it is very unstable because this one acting as a electron donating group. So it will keep on pushing electron density towards the oxygen, making it more negative, and more negative, very unstable. Okay, unstable, and hence least acidic. Okay, for this one, carboxylic acid is going to be the most acidic because it involves the delocalization of electron in the two electronegative atoms. For example, the oxygen atom here. Okay, and this one going to be in the middle because it involves the delocalization inside the benzene ring. Okay, so for the explanation, we can say that the carboxylic acid are more acidic due to the resonance stabilization of the carboxylic ion. And we can say that the electrons in the carboxylic ions are delocalized between the two oxygen atoms, which involve two electronegative oxygen atoms. Okay, and whereas in the phenoxide ion, the electrons are delocalized in the benzene ring. Okay, that's what you have seen in the chapter hydroxy compound. And the C double bond O group is an electron withdrawing group, which reduces the electron density of the OH. Okay, see the word O here. So the electron density of OH is going to be reduced, and hence the OH bond gonna become weaker. Thus, the H plus ion can be easily donated and make the carboxylic acid to be more acidic than phenol and alcohol. Okay, so I think that's all for today's video. See you again some other time. Bye!